Okay, got it. And so we will divide this tutorial in, but it won't be strictly speaking, it won't be a tutorial because I think I haven't asked you to install the software. So we can after the tutorial we can I can explain you how to install the software and how to use it. So I think we will divide the tutorial in two parts. So I will start to explain what is a Laue diffraction technique, what we can obtain. I will show you a demonstration of the software we have been developing since for maybe a decade or several years. And the second part will be devoted to the new tool that Larvae has developed recently. And this new neural network-based indexation program will allow us to analyze quickly the data. So let's begin. So I'm going to share my screen. What could it be? This one, share. The main desktop, yes, will be enough. This one, okay, share. Yes, that's good. And then going to presentation view. Yes, why not? Okay. So, what is Laue diffraction? So, during this tutorial or webinar or seminar or presentation, you can ask your question in the chat if it is possible for you, or you can interrupt me and to ask a question. I think it should be also better, but don't hesitate to ask question. And Ravi will be able to follow the chat, and then if we have many questions, we can stop the presentation, and then I can answer the questions. And so don't hesitate to ask questions. I need some interactions to stay focused on the presentation and to give you the most of the informations. So simply what you can see, if you can see my mouse here, this is a typical Laue pattern. So the intensities that we can record on a plane or curved detector. In our case, it is a plane detector that we put close to the sample, and then we illuminate the sample with a polychromatic beam, so a multi-wavelength beam, white beam, and this is typically the scattered photons that have interacted with the lattice planes, and then they have been reflected by the lattice plane, and then we can measure these Laue spots, and the last Laue spots are forming Laue pattern. And you can do such kind of a measurement in any point in your sample. And this is typically a polycrystal of CDT. And from the analysis of every single Laue pattern that you have been collected in every sample position, you can determine the orientation, the local orientation there, and also the strain, the local strain from the unit cell of the material. And what is recent? So this is a two-dimensional map. And this is really the standard measurements we can do really fast. And if you have time for your proposal, for your experiment, for your studies, you can also perform some 3D map of the sample with an additional technique that allows you to have the depth resolution inside the sample. Then you can reconstruct every Laue pattern in any voxel in your sample, and then apply the standard analysis to determine the orientation, the local orientation, and the local strain. So I'm sorry, I haven't really updated the PowerPoint presentation, but the information hasn't changed so much in 1 year. Okay, so how to become a good Laue practitioner? So you will need to know a bit of mathematics, and but it will be simple mathematics, just to explain what is a reflection and what is a geometry, which is related to the how we can express the reflection onto a plane, simply like that. I think most of you know what is a reciprocal space. So I will just show you what are the schemes, or what are the schematics we need to understand the Laue pattern. And so you will be able to construct yourself a Laue pattern on your own, on your computer, if you want to. And then I will also show you what are the current experimental capabilities on the beamline, and also on the beamlines in the world for the Laue diffraction technique. And I think this is yes. And the second part will be I'm going to show you what is in practice, what is the analysis of the Laue pattern, and I can already tell you that there are three main steps of the analysis. So this is so you collected some images, so you need to do some peak search, so to find the location, precise location, accurate location of the Laue spots on your image, and also or your images. So we need to do it automatically. And the second step is the indexing. It means that we need to know, to find, to recognize what are the HKL Miller indices of a certain amount of Laue spots in your Laue pattern. From the indexation or indexing, we will be able to determine the crystal orientation. And the last step is devoted to the refinement of the model, a simple model of a single crystal, and we will allow the crystal to move a bit in terms of orientation, and also we can also stretch, deform the unit cell in order to fit the Laue spots positions. And there are also a final step of post-processing. Then you have to compile all the results to do beautiful 2D or 3D maps. Okay, so in history, so Laue, I think you may know that Laue diffraction is the first technique that has been used in the past to evidence that there's something going on in terms of interaction between the X-ray beam, this unknown X-ray beam, and the crystal. And then the team of Laue has performed this experiment. So putting a single crystal there and putting close to a raw X-ray tube at that time, and then this is what they measured on the photograph film, and clearly we can recognize that there's something discrete and not continuous. So there could be a relationship between the crystal and the X-rays. Now, actually, a few years later, they improve largely the experiment and the instrumentation, and then this is a Laue pattern they collected from crystals, and clearly we can distinguish the Laue spots. And also we can also see the symmetries in the crystal. So from these first experiments, so clearly the relationship between the crystal so there was some similarity between the crystal and a 3D grating, and also it was more obvious that the X-ray has a wave in nature. Like the light. So Max von Laue got the Nobel Prize for that. Okay, so now today, so more than one century later, we can still use the Laue diffraction as a Laue macroscopy, because now we are able to, thanks to the ESRF and also the advent of optics, of the X-ray optics, we are able to provide a micro-focused wide beam on sample. We can also move the sample vertically and horizontally, and then it is really now a microscopy, and the signal we are dealing with is the scattering signal, is the Laue pattern. So, as I said, we can collect a Laue pattern in any specimen position. So in a one X-ray shot, we have one image, and this image can be the superimposition. So this is a sum over the crystals in the samples. So inside the probed volume, because the X-ray can penetrate more or less deeply in the material. So we can, in a single image, we can have the addition, the superimposition, incoherent addition of several Laue pattern, and each Laue pattern comes from a single crystal. And obviously, we just don't want to do just one image on the sample. We want to have statistics to understand better the material behavior and the structural properties. So we will do a scan of the sample. So in 2 dimensions, this is really the easiest way to do it, because we were sure to be able to analyze the data in a larger accuracy. And so the Laue diffraction technique is a scanning technique, not a full field technique. This is a scanning technique. And to summarize, so this is really a technique which is very suited for the analysis of some microstructures. And so to look, to observe, to measure the phase, so the crystal symmetries or the crystal nature, and also to determine the orientation and the strain, as I said. And we can have an idea of the position. Clearly, we can find the position in the position of the grain, but also we have an idea of the shape thanks to this scattering signal. And also, what is very interesting, and this is at the border of the use of this technique, is to study the defects, the crystalline, the lattice defects of inside the crystal, so the extended defects. And so we can locate the region where the Laue pattern is a bit disturbed, and so we can locate these regions, and we can also, this is model dependent, but we can have also an idea of the nature, for instance, of dislocations density, so the number of dislocations inside the material, but also the directions of the dislocations. So still to summarize, to give you an idea of the technique, so we can, on the beamline, put a polycrystalline sample, or we can put a single crystal, a single object, and that can be for sure that can have many grains inside. And we can probe with the X-ray beam. We can probe the structural properties. So this is a micro Laue scanner. So the beam size on the beamline is for sure less than 400 nanometer, and you can move the sample to explore millimeter sample. So obviously, you can't. It's not reasonable to scan the millimeter sample with a step of 1 micron. But you can choose different regions of your sample. And also, there is another asset is that you can perform some in situ experiments or operando experiments. And then what you can extract with a high resolution, 10 to -4, in terms of angle and strain, you can determine the orientation and the full strain. I have put the full in parentheses, so I will explain you later why. And recently, we can also do 3D map and then you can locate the defect inside the material. Okay, so this technique is available in France at the ESRF, but also in US. There are two beamlines in Chicago, in ALS and APS. One beamline in Canada and also a new one in Taiwan. Okay, how it is done on BM32 beamline. This camera is now we have a new camera which is black, but this is more efficient than the CCD technology. Now we have a SCMOS, scientific CMOS camera with a smaller readout time and smaller also noise. So this is perfect for our experiment. And this camera is looking at the sample that you don't see, but the sample should be there. And you've got also a fluorescence detector that look also at the sample. And in order to perform such an X-ray fluorescence map, so it's not mandatory to perform the fluorescence map, but it's a marvelous way to locate your sample of interest by fluorescence. So because you can't, so at the beginning of your experiment, you can do a visible light microscopy at the surface of the surface of your sample to select the region of interest. So the microscope, this is the objective, and the camera is taken this image, and then if you want to do the visible microscopy, you have to put the microscope down. So you can't have in our beamline and also in other beamlines, you can't have at the same time the visible light microscopy and also the Laue microscopy. So you have to do in an alternate way. And so, as I said, the energy bound of this beamline and also of the three major beamlines in the world is from 5 keV due to the Beryllium windows up to 22, or it depends on the beamline, 22, 25 keV. So that's good for that. As I said, you can do some 2D mapping of the raster scan of your sample, and you can have several types of objects to look at. You can do some in situ experiments, so you can heat up the temperature for sure. You can also apply a mechanical load, so you can many users have used now mechanical test machine, and then you can follow the structural evolution, the evolution of the structures of your material. And this is more advanced compared to the standard Laue diffraction that we can perform with the beamline, and you can also perform the full stress determination to assessment in your sample. So for that you need if you want to do it experimentally, you need to do the measurements of energy of the Laue spots. I will explain that later, why it is not available in the standard analysis and the standard experiment. And if you want to do a 3D mapping, you have also to do an additional measurement that consists in moving an absorbing wire close to the surface, and then from that you can have a depth resolution from the data you are recorded. Okay, so where is Laue diffraction? So Laue diffraction is let's say it's a combination of X-ray diffraction. So you can get information from the crystal, the atomic structure, but not a part of it, let's say. And for sure, you are going to look at the defects, the structure of the material at a larger scale, and also you can do some 2D and 3D imaging from the compilation of all the images and all the data you will collect on the beamline. And this is really suited for the study of microstructure, because you with X-rays, hard X-rays on the beamline, you can penetrate on the sample, so you are not limited to the surface, to the first nanometers of the sample. For example, if you are making electronic microscopy, the probe volume is very, very small compared to the volume you can access with X-rays. So thanks to that, you can really study real materials in situ or apparendo, and looking inside the materials, which is invisible by other techniques. Okay, for people that are more familiar with mechanics, I think it's good to compare this technique with the EBSD. This is electron backscattering diffraction technique that is more or less quite available on every SEM, so scanning electron microscope. And then this technique, EBSD, can also provide orientation map and also a strain map. But the advantage of X-rays are that X-rays can penetrate more inside the sample. You need to have less sample preparation, because even the first nanometers are really disturbed, or because you have due to the preparation of the sample. So the main signal is still safe, and then you can really study the structure. And also you can study conducting or isolating materials, and you have a finer resolution in orientation and strain compared to EBSD, because as I said, we have 10⁻⁴ resolution. So for sure, you need still a synchrotron beamline, and this is an old slide. At that time, I said that further accelerated acquisition and mostly analysis should be provided. And now Ravi will present you the first results we have to really accelerate the analysis of the data. Okay, this is one slide to show you what we can obtain, and this is the main keywords of the technique. So this is a take-home message. So a strain orientation resolution, which is very, very fine, 10⁻⁴. You can perform some strain map on the sample. This is, for instance, a germanium strain membrane, and so a biaxial stress applied to this germanium membrane, and then you can see that we can measure the finely what is the distribution of the strain. And this is in very good agreement with FEM, finite element analysis results. And okay, you have a high spatial resolution, so less than 1 micron. There, the missing micro, and you can do some in situ, and you can have quite valuable information of the crystalline defects in the materials, and you can also perform some 3D measurement. Okay, now we are going to I'm going to explain you what is that Laue diffraction is quite simple, and you don't need to do so much university studies to be an expert. So you just have to understand that materials is made of a lot of mirrors, and the mirrors, each mirror corresponds to a set of atomic planes defined by the HKL Miller indices. So just to understand what is the mathematics behind the reflection. So this is if you have the incoming beam there, and this beam is reflected by the surface, and the surface is defined by the normal. Then you can have some relationships between the incoming vector, the outgoing vector, and the normal. of the surface. So you can do some mathematics, and this is an elastic process. So the norm of the incoming vector is equal to the norm of the outgoing vector. This is this relationship, and so whatever the normal of the crystal, you can always have, for instance, this relationship. If you know the normal of the vector, if you know the direction of the incoming vector, you can predict, you can calculate what is the outgoing vector. So given Q and UI, it's easy to construct the reflected or scattered beam UF. So now, as you know, so we now the lattice planes are not always parallel to the surface of the crystal, of the sample. And then you have, so now we will consider that the Laue diffraction, it is like a Bragg refraction. It's a reflection onto atomic planes. And then I've got still this incoming wave vector now, wave vector defined there, 2 pi over lambda. And these photons comes from the right, and then they are reflected by the atomic planes, which are defined by the normal Q. And the Q, it's related to the reciprocal space that I will show you in the next slide. And KF, it is the outgoing vector. And you know that the angle, the incoming, the incident angle is equal to the outgoing angle. And the scattering angle is an angle between the incoming beam and the outgoing beam. And this is a 2 theta, and this is for people working in scattering experiment. This is the 2 theta angle. So the scattering deviation, the scattering angle. And now, if you do the same mathematics than before, you will have such a relationship between the wave vector. So the outgoing wave vector is equal to the initial one plus something which is along the direction given by the Q vector, the normal of the surface, and the amplitude of this shift between the two vectors depends on the norm of the Q vector. So given the Q vector and the incoming beam vectors UI, we can calculate the KF vectors. So it's really it's nice to understand that, just because it will help us to understand in a handy way what's going on in the material as soon as you can stretch the material and you rotate the material. So it is a really simple and nice description of the mathematics and the geometry of the reflection. So another sketch which is very useful, if I give you a Q vector, and you know that this will be the vector joining the origin of the reciprocal space to a node of the reciprocal space. If you want to know what are the photons that can satisfy this relationship, then I need to know the norm of the Q vector and also the norm of the KF. So I know the norm of the Q vector, but I don't know for the moment what are the I know the direction of Ki, but I don't know the length of Ki and Kf, and I don't know the direction of Kf. So to compute Kf, so you take the line in between perpendicular, so mediatrix in French, and you compute this line, and now you know the origin of one point of the vectors Ki, of the starting point of Ki and the starting point of Kf. So this is very, very simple and useful to remind. Okay, now I'm going to show you that if you do a scattering experiment, you must know what is a reciprocal space. And for any crystal, we can crystallize a crystal. We can have an associated space, and every atomic planes can be represented by a node, a node in reciprocal space. Now this is the black spots, the black nodes that are represented there. And for instance, I've taken an arbitrary crystal. So there you have A star, B star. B star is pointing towards us, I think, and C star there. And then I have represented the two evolved sphere. So this sphere there corresponds to the minimum energy we have on the beamline, and the larger sphere there corresponds to the highest energy photons available on the beamline when you do some Laue experiment. And simply, if you we will do such, for instance, if you want to calculate if you want to predict what could be the outgoing vectors coming, outgoing photons coming from the reflection onto the 202 planes in the sample. So you assume that the photons are always coming from the right there. This is the direction of Ki. So as I said, you compute the metatrix there, and at the middle you calculate the perpendicular line. Tac, you are here, and then you have you know now this is a Ki in red. So you know now the length. So the energy of the photons that can diffract, that can reflect onto the 202 planes. So this is Ki and this is Kf. If you do the same for the 303 node, so you compute the metatrix, and then this is the starting point of Ki. Now the color has changed because the energy of the photons will change. And then this will be the blue Ki, and this will be the blue Kf. So as you can see, you have the direction of emission of the direction of reflection of Kf red and Kf blue are the same. So you can't. So it will, and these photons will going out the sample. There, this is a red, and this is a blue, and they will hit the detector at the same position. So the conclusion of that is that a single pixel or a single point on your detector corresponds to a direction in reciprocal space. So all of the photons that we imagine, you can imagine that the detector is there at the top of the screen there, and then all the photons that will be reflected on the 202, the 101, also the 303, and they will hit the sample, hit the detector at the same position. So we have a real mapping, so bijection, in mathematically speaking, between one reciprocal space direction and one Laue spot or one pixel on the detector. This is written there. So what are the advantages of that? And so it means that whatever the orientation you whatever the sample, the crystallized sample you put on your sample holder, as soon as you eliminate with the wide beam, you should collect many spots, and then so it's very nice. You have always signal when you use a polychromatic beam. So contrary to a monochromatic beam that on single crystal, you have to orient your crystal and your detector to find the Bragg reflection. With the polychromatic diffraction, it's easy. You put the sample, you open the shutter, and then you will have a Laue pattern on your detector. So you've got also a large number of Bragg reflections. So for those who are very interested in having statistics, or so it's a nice asset. And also, you don't need to rotate the sample. And this is, as a conclusion, this is for sure, this is an easy way to find the orientation. And this is in the past, and I think you in your studies, in the university, you have used the Larvae diffraction just to orient a crystal before making other characterizations. Okay, so now I'm going to show you what the thing will look like when you will use the software to simulate and to analyze the data. So these are the main convention in order not to be lost. So for instance, the sample is there, and we have put a camera at the top of the sample, and the beam is coming from the right, and this is the frame I have chosen to express the mathematical properties of the mathematical objects, vectors, and so on, matrices. And then from this sample, this is silicon wafer. So the Laue pattern we will use to that are recorded on the detector correspond to the photons. This correspond to this geometry. So pixel X. So the horizontal direction corresponds to the horizontal direction also, and the vertical direction corresponds to something which is quite parallel to the X direction. So the camera is not so tilted in reality. Obviously, we try to put the camera as much as perpendicular to the sample, to the incoming beam. Okay, so another thing that I want now to explain is that we have seen that there is a mapping between any direction in the reciprocal space and a pixel on the detector. So there, I have considered all the spots there, and I have computed all the directions that correspond to all the spots there, and each direction can be projected on a big sphere, and this is this presentation. There, the yellow sphere corresponds to a sphere centered on this point, and you can see that if I project all the directions onto this sphere, we can see, and so each black dot corresponds to one direction, and I repeat, one direction can be composed of many reciprocal space nodes, and if you do this computation, you can see that there are some spots that seem to be aligned, and this is what we are calling zone axis. And what is important now to understand that if I rotate the crystal around the origin there, obviously the black dot will rotate around this point, and then all the directions will also rotate. And if you do so, you may see that the black dot will rotate around along the surface of this projection sphere. So what is important to understand is that the absolute positions of the black dot, because the camera will collect, for instance, this part. Well, you have some red spots, and this is the experimental red Laue spots. And so the camera is catching this part of the information, but for sure the X-ray photons will be scattered in all directions. But we are catching only a part of it. Sorry. And then from the absolute positions of the Laue spots on the camera, we will be able to derive the orientation of the crystal, and this is This is the key point of the technique. If you know the positions of the spots, you can measure, you can determine the orientation. And also, if you look at the tiny shift of the blue spots with respect to the reference simulated Laue spots. And then we can also measure the deformation of the unit cell. So zone axis, maybe if you have questions, I can. So what can be said that we can see some apparently aligned spots. And you can, in the Laue pattern, this is really beautiful. And also you can see that the main low HKL spots are at the intersections of dense zone axis. And also what is interesting feature is that around low HKL Laue spot, there is a desert of Laue spots. And in the past and also today, we are still using this low HKL to orient the crystal. So if I want to orient my crystal along the 001 direction, I'm going to try to put to change a bit the orientation of the crystal in order to, for instance, to put this 004 reflection at the center of the camera, for instance. And if you are expert, you can also deduce rapidly that okay, the crystal is oriented 111 because you at the center of the camera you have the 111 on the detector. This is the same for the silicon 100. We can see that here you've got a fourfold symmetry, and this is a 100 reflection. And here this is a 110 twofold symmetry spot. Okay, so yes, this is there is an interesting. I'm going now to explain something which is quite advanced, but that can be useful also. So this is a Laue pattern, a typical Laue pattern you can connect on your detector. And as I said, you know the mapping between each Laue spot, each pixel, with a point on the projection sphere, because one spot corresponds to one direction in reciprocal space. And then if you can imagine that now if you project all the directions onto a plane which is tangent to this sphere, now you can see that what was aligned on the sphere is now aligned on a plane. That means that now this is a typical two grains Laue pattern that has been projected properly onto any gnomonic plane. And you can see now that the zone axis might be this one. There is no correspondence, but you can trust me that this zone axis may correspond to this one, for instance. And this one may correspond to this one. So it's a way to represent the data in order to disentangle the information, to recognize that these crowded Laue patterns there. You can imagine that you have many spots, and then it's a way to distinguish, to separate, to segment the Laue pattern. Okay, now there is an important point that I want to mention, that the Laue pattern, so as you may understand now, has got a lot of advantages. But there is one drawback in the standard measurement and standard analysis, that the Laue pattern is not sensitive to all the deformation of the unit cell. So you can't determine the six latest parameters from the analysis of the Laue pattern in the standard way. So why it is so? So if I simulate a two-dimensional crystal, and you start from this blue lattice, and then so you can now, as I said, you can predict where will be the projection. So I have computed all the projection there. So this will correspond to 3 spots on your detector, for instance. And now if I start to stretch, to compress the blue unit cell, and then I end up with this red unit cell, and then I can now simulate compute where are the red nodes, and you can see that the direction of the directions of the reciprocal space, the directions have changed, and then we will measure that on the detector. So there is clearly for this transformation, clearly the Laue pattern will be changed, and we will be able to measure that, and we will determine from the measurement of this angle, we will determine what are the transformation from the blue to the red. But however, if I perform from the blue to the red one a nomothetic transformation, you will see that the directions are unchanged, and then it means that for homothetical or volumic or non-deviatory strain, the Laue pattern can't distinguish between the Laue pattern from the blue net and the red net. So this is the conclusion. So the standard Laue diffraction is sensitive to the deviatoric strain. So it means the angular distortion. You have your unit cell. If you apply a share transformation, if you share your unit cell, okay, the Laue pattern will see that, and you will be able to measure the amplitude of the share. So for crystallographer, it means that you will be able to measure only 5 parameters over the 6. So for instance, you can decide to say, okay, I will fix the A parameter, the A length, and then the analysis of the Laue pattern will give you only B over A, C over A, and the 3 angles. What we can do experimentally, we can measure the energy of one spot. It means the length of one spot. And then from that, you will be able to know the A value of the volume of the crystal. So now with this additional measurement, you will be able to measure the difference in volume or the length between the blue and the red. So that means that now with the measurement of one spot energy, so actually we are measuring more than one spot energy, and for statistics, and then you will be able to measure the full set of lattice parameters. So the full strain tensor, all the component of the full strain, and then also if you know the full strain tensor, you know, if you assume that you know the elastic constant, you will be able to compute the local full stress tensor. So X-ray diffraction will always give you deformation, and then if you assume that you know the elastic constant, you can compute the stress, and the stress is very important for engineering. Okay, this is to sum up what can be done on the BINOM. I think it's already clear. It's already clear also. And now maybe I can show you what time is it.
It's almost 10 to 10.
10 to 10. Okay. Now what I can do maybe is to show you the software, and then just to introduce. Yeah, because the idea is to. I'm going to finish at 10:15. Okay, so going now to the software. I'm going to share again my screen. I think it's this one again. Share. Yes. So that's okay. You okay. You have everything now. Okay. So now I'm going to show you what is a Laue pattern. So I can go to the example, for instance. No, I'm going to find images. Sorry. So images. They are there. Laue images. For instance, this one. Talk. So I have used at that time it was another camera. Okay, and now maybe I can do that like this. No, okay, is that not possible? No, yes. Okay, so as you can see, this is a Laue pattern, a null Laue pattern that we have, for example, measured 10 years ago, and another camera, but the main features are there. You can see there are some spots, and you have also the fluorescence background. And the idea of the analysis, as I said, you have 3 steps. And the first step is to find the spots position. So you could if you can zoom, for instance, and this is quite tiny. So in this case, the peaks are very small and they are round. And what I can do is to click and press fit, tuck, and then you have the position of the peak by using a model of a 2-dimensional Gaussian, and we can do this automatically actually. Okay, so it's not working because the threshold is not well set. So I can play through the threshold, and then I've got 58 peaks, for instance. If I'm trying to catch maybe this spot, because these spots haven't been found, so maybe I can try to decrease the so 80, and this one still not, and maybe if I decrease and now too many spots to fit. Okay, so the idea is to maybe remove the background there. So we have some procedure to remove the background. So I have subtracted the low frequency image, and then now if I use this intensity threshold, I should find everyone. No, still not this one, or maybe this one is very, very, very small. No, why this one is not found? Okay, I don't know. No, okay, or maybe I can play to the. It's just to show you that we can find a way to we have several parameters to play with in order to analyze one image, and the idea then we can save all the parameters that are used for the peak search. And then we can apply the same parameters for a set of thousands images. So now I'm just want to maybe I don't know. Maybe this one should be okay. Talk? No, not yet. No. Why? No, why is this? Why? I don't know why. Talk. Maybe this one is too round. Well, okay. Because this peak was so the size of the peak was so small that at the beginning it was rejected. Okay, so now we have let's say I have my Laue pattern for the rest of the analysis, So, okay, so normally it is saved, so I can quit, and I can go to, first we need to calibrate the geometry, and it will be also a way for me to show you what are the different Laue patterns we can, so I can import the data I've just collected, it is there, Laue images, engine, modified, and this is, no, it's not. Yes, it is. No, it's not. It's not today. Okay, it was okay. No, alors, voilà, it was actually in this. Voilà. Alors, it is. No. Voilà, the last file. This is this one. This is the list of people. Okay, and now I'm going to. So this will be our data. So maybe it's not so easy, but these are not our data. Maybe in X and Y position. So maybe you can recognize those field circles are the experimental data, and the hollow circles are the simulation. What I can do is to rotate the simulation like this. Like this. And the idea of the indexation is to match the experimental data with the simulated data. So I know that this is a germanium 111, so normally I should put at the top, I should superimpose this spot with this one. And now I can also rotate around this axis in order to try to superimpose the two Laue patterns. Now, since the parameters are not good of the camera, because the camera is not well set. So for instance, if I change the camera position, you can see that the Laue pattern. So if I, for instance, if I decrease the detector distance, normally the Laue pattern will be very, the experimental one will be very big. Okay, it's not. Oh yes, what is changing? It is the simulation. Okay, maybe it's not so. So I know that the distance we can measure on the beamline. So that the distance between the detector and the sample was close to 69 at that time, and then you can see that I'm close to maybe close to the solution. And so I can try to automatically make the links between the two Laue patterns. So every pairs of spots which are close enough can be considered. So I will stick all these pair, all these spots forming a pair, and then I will try to minimize the distance between the minimize the distances in all pairs, by changing a bit the orientation of the camera and all of the distance of the camera, and also the orientation of the crystal. And this is what I'm going to do. So automatic links, and then I'm starting to fit. And normally back, and then now I've got. So you have things that the latest the calibration parameters of the camera has been refined, so I can do several loops to be sure. Right. So I think yes, it's finished, it's over, and then we have a perfectly. We can look at the quality of the matching. So the matching, for instance, there is a discrepancy between the experiment and the simulation, and the best model, and the best crystal, and the best camera, and then you can see that the discrepancy is less than 1 pixel. So it's a fraction of a pixel. So you have this result. This is the mean residue calculated over the 95 pairs. Okay, so we have our parameters. We know where is the camera, and then we know perfectly. We will be able to compute the 2 theta and key angles. So we will be able to compute the scattering angles from any images that we will collect. So this calibration part is done on the beamline and on reference sample that we know perfectly, that are unstrained. Okay, so I have shown you the calibration part, and now we are going to try to index a Laue pattern. So I'm going back there. Just up, because there is a default data. So, for instance, here, if I want to index a germanium that has been collected, this is allowed. Now we have the list of spots from the big search, and we want to index this Laue pattern. So it can be this is in scattering angles space representation, and we know that this one should be the 111. This is a germanium, unstrained one normally, and we know that this is a 111. But we have to say the idea of the indexation is to recognize the angular distance between two spots. And then we have a lookup table from a reference, germanium reference, or diamond reference, or cubic reference, and so we know quite a large number of angular distances between two spots in a germanium, for instance. So the idea is to if I just want to the angular distance between this spot and this spot, it is 29 degrees, 0.5, and then this distance will be compared to a database of distances, and then maybe it is a distance, the angular distance between the normal of the 311 and the 111, for instance, could be. And so this is what I'm going to do now. I can click on that and click on that. Okay, and then maybe I can show you. Yes, okay. And this is all the possibilities that he has found. Yes, this is. So for instance, this I have clicked on the spot number 0 and the spot number 32, and the spot 0 can be the 1 minus 1 1 reflection, and the 32 spots, the spots 32 could be the 3 minus 1 1 reflection. And if I simulate the Laue pattern, taking into account this hypothesis, then I have found that there are 96 spots or directions of the Laue pattern that match the experimental data. So this is this solution. So I can show you what is this solution. So it is the star correspond to the experimental spots that has been found from the indexing procedure, and the blue field circles correspond to the experimental data. So you can see that a good matching. So if I'm just looking at a wrong result, so a poor result, only 12 directions or 12 spots are matching the experimental data. Yeah, you can see that the red Laue pattern is sometimes there is a matching there. There should be some 12 matching somewhere within a certain tolerance, but you can see that the result is poor. So we have a mathematical way to quantify the closeness, the proximity, and the matching, the similarity between two Laue patterns. And this is what we will use for the automatic analysis. So if I'm plotting this one, I can now compare. I will be also to do the automatic links. So all the spots that are close enough within this 0.5 degrees, I'm going to use them for the next refinement. So what I have shown is the indexing, and now I'm going to do the refinement, the third step and the final step of the analysis. So using these automatic links, we can have an idea of the links that have been done. So spot number 1, experimental 1, is close to the theoretical spot 2, and the theoretical spot is the 422. and the experimental one spot has this intensity, and the residues, the current residues, the current angle between the two normals is 1/100th of degrees between. So we are considering all this. So you can see that even this one, so this pair has zero residues. And the idea will be to find what is the best crystal orientation and the lattice parameters, the 5 lattice parameters that will minimize all these residues. So this is done simply by clicking on refine, and these are the results. So we were starting from the initial lattice parameters, and these are the final lattice parameters. And as I said, we have to fix one parameters. So generally, we say that the A parameters is unknown, but we can say that okay, it is something which is close to the textbook's value. And what is refined really? This is a ratio B over A, and then this is a B value by considering that A is equal to this value. And so we have refined B over A, C over A, and we have the final value of B and C, and we have the final values also of alpha, beta, gamma. And you can see this is the orientation matrix, and this is a deviatoric strain. So it means that in 10⁻³ units in crystal frame, and this is a deviatoric strain. So in 10⁻³ units, so it's a 1/10% unit. And now you can see that the germanium is very, very unstrained, and for sure because it comes from the microelectronics factory. So this is and we are using it for reference Laue pattern and calibration. Okay, so now you know more or less everything of the main step. What I can show you is that if we want to deal with polycrystals, and because here it's easy, we have a single Laue pattern, we don't have to use a new software that so LaueTools is not really useful because you have many software to analyze a single Laue pattern. But the idea of this software is to deal with polycrystalline samples. So I'm cleaning everything, and we are looking from polycrystalline samples now. So a Laue pattern that is composed by, maybe I should have some examples. Yes, good. I don't remember actually. Or maybe I can start. Yes, with this one. I'm not sure. Maybe implanted. Yes. Okay. Donc I'm taking an image. Sorry. So getting back to. I'm going fast just to let Ravi show the no network. And so we are open. So we will do. As a user, we have an image to analyze. So we have collected images. So examples, YouTube implanted. I take this one from 1996. It was at that time MACCD, NK, and then what is it? Okay, I don't know what is. There's some strange. Okay, so forget for that. I don't know what it is. Correlated file maybe, but you can see that we have plenty of spots, and it comes from polycrystal. Actually, because I'm a bit expert, I know that there is I think you can see there is there is a zone axis there, and this is an important spot. Then this spot should be a low HKL spot, and you can imagine that there are some zone axes going that will intersect at this position. Okay, so we perform the picture. So we try to do the thing blindly. So it's trying to calculate. Okay. Maybe I'm gonna take another one. Maybe this one. I don't like this one. I don't know why. Alors, Laue, it was Laue images. No, it was examples. Sorry. Planted. Voilà. Point. Hop. Alors, yes. Oh, this one is better. Currently. Well, okay. So another image, another part of the crystal, that of the microstructure. We have almost maybe one or two. Okay. So I'm going to try to find all the peaks, and we want more than that. So I'm going deeper with the threshold. Okay. So maybe at some point I need to remove the background coming from the L alpha or beta or gamma of the uranium atoms. So search all peaks. Okay, now I can decrease the threshold. Yes. Okay. Okay, maybe I can also. Yes, I would expect 1,000 peaks, but I think there is another image for that, but I'm not able to find it. Okay. Okay, it's 637. Why not? Okay, let's say just for the principle. Okay, so we have our image. We are happy with that. We have, but you can see there is still peaks to find. Huh? Okay, so this image is saved. Normally, I can quit. I can go now to the indexation process. The idea is to find where this image should be, and I need to. Okay. So the easiest way will be to go out just to find the proper folder. So indexation, and now no, it doesn't, because I think examples. No, maybe we are here. Okay. No, c'est bon. Alors, last modified. No, it's not today. Oh no, it was. It is. Attends, c'est dans Anaconda. C'est petit. C'est dans Micha. Anaconda. Non, c'est working exact. Anaconda 3. Alors, voilà. I should have more. Attends, c'est quoi? C'est bon, librairie, oui, c'est ça. Non, c'est Hans. Voilà. Python 7. Library. Python somewhere. Yes. C packages. Okay, so normally if you are collecting data, it's easier to find them back. Okay, and now LaueTools examples. No, alors. Okay. I haven't saved the images. Okay, that's strange. I haven't saved the files we have produced. So examples. It was you. Well, no. So I need to do it again. Okay. Alors, 80. Ouais. Alors, moi, c'est CD. OK. Alors, remove the background. Poof. Going to something small. Voilà. And save the file. It is saved. Maybe YouTube. OK. Poof. OK. Where are you? Back. And now going to the open pick list. Oh. OK. Donc, examples, you. Yeah, you are here. Okay, that's good. Okay, right. Okay, tac. So we have and we will find the proper calibration file for the good camera position for that. I set that. I set, and then we have now we have if we are looking at the Laue pattern, and this is our Laue pattern. Okay, so we could try to index manually for pedagogical reasons. So maybe I can try to maybe this one may be important and this one, and it works. Okay, it works. But okay, we are lucky. We have found one grain. The idea is to say that maybe it will be better to let the computer calculate a large number of distances between several spots, and then we will find also results. So this is the automatic indexation. I let the computer to say, okay, compute among the 5 first spots, try to find a distance to be recognized, and with the U2 structure. Start. So he's computing something, yeah, and then he found some result. Okay, maybe I can show you 2 results. So this is a bad result, but you can see that could be if you have many spots in your Laue pattern in the blue spots, then you could have a good matching rate, but it would be a wrong indexation. So here it's a good indexation, and we can refine, and then if I'm happy with that, I can tell the computer now you will remove all the spots that have been indexed, and then I will continue by maybe the energy was higher at that time. So replot, yes, and automatic links, yes, and refine again. And now I will remove the indexed spot, and I will restart the indexation of the remaining spots to be analyzed. So ascent matching block. And now, if I'm looking at the Laue pattern, we have less spots. We have now 500 compared to the 637. Yeah, we had at the time. And then I can redo the indexation like this. So U2. To file. So in this case, it's quite easy because the unit cell is subcubic and it's not so difficult. Okay, and then I can do again 25 replot, auto links, refine, and I've got a second crystal and it is refined, and then I can accept. And I can go further for the analysis of the remaining spot. And then you can proceed like this to index all the crystal you have probed in this by the X-rays at this specimen position. Okay, maybe I'm just finished to show you. A bit the capability of the technique. So, for instance, what can be done there? Maybe you can do a presentation mode. Yes. And this is experiment where you with a single shot you have an oxide U2, and then at the top you had a layer of U3O7, and you had 3 variants. 3 possible variants, and then it was just by making just one shot experiment. It was we were able to measure to evidence these 3 possibilities, 3 crystals, and also that the strain, the ratio C/A was 3%. And so LaueTools is also able to find the
So in situ, you can eat up the sample, and you can see that the Laue pattern can evolve, and you can see also you can have an idea of the defects that appears or disappears. Okay, this is an estimation of the strain again on this UO2 material at the function of the orientation, and the results were in good agreement with the simulation and the model. And this is to explain you. So we can do a map. So in situ map, you can do a mechanical test, and you can measure how the microstructure evolves. And you can, this is now quite old measurements, but you can analyze the data and find the strain or the orientation as a function of the load. You can do some in situ experiment also. You can compress your pillar, for instance, and by mapping by doing a map on your sample, you can locate where are the defects. So, for instance, when you have defects, it means that the Laue spot will be elongated, and then from the measurement of the direction, you can have an idea of the slip system that has been activated. And you can also measure an estimation of the dislocation density. Maybe I think we can. I think I have many things more to do. I think we can do a pause before going to the review presentation of the neural network, and maybe before the pause, if you have any question, maybe it's a good time to ask them.
So Sebastian, there is in chat two
Okay.
questions which haven't responded. So the first question is, can this technique also be applied to low Z compounds, example, organic compounds?
No. So yes. So due to the spectral bound of our beeline, we are using 5 keV to 22 keV X-rays. Low Z materials, they don't have many electrons, so they don't really provide a large signal of scattering. And I would say that if you can, if you expose a very long time on, even I think on graphene, I think we have seen something, but it's difficult to see something. So if you want to see a carbon, for instance. First, so the Laue signal is very sensitive to the intensity of the Laue spots is depend on the volume you probe in your sample, and the number of electrons, so the electron density, and also the disorder. So I think if you, for instance, we can have a measure. We can measure the diamond, the Laue pattern of a diamond, but because the diamond is so well crystallized that you can still have a Laue pattern. But for example, for graphene, we have tried to find. So it's a two-dimensional. So it's a very thin, ultra thin material, and the carbon is has not so many electrons to be used for the diffraction. So I think we spend a lot. We should expose a very long time, and the result was not so evident. So, but except the carbon, I think we can measure titanium. So and I think the minimal, except the diamond, because the diamond is so well crystallized. I would say that I think the lowest Z material has been the titanium, could be, yeah. But I think we have also measured. We have we have used recently a beryllium. A furnace which has a beryllium window, and then we have seen the Laue pattern from the beryllium window. So, so if you have a big grain, so it's alright. So the signal depends on the volume and the disorder. So the best answer would be it depends. It depends on your material. So maybe if you can precise your, if you have a material in mind, maybe I can help you. But well, feel free to contact me to tell me what is precisely the materials you want to study.
So the other question was from Subsection. She's asking if Larvae diffraction is a good option for protein crystal. Protein crystals.
Yes, I know. Yeah, it's a good question. Here on the beamline, we have already tried to do some protein crystallography, and we had a cryo gun to make the sample cold enough. Actually, the best geometry for that we did that. If you have maybe I haven't clarified that, but we are in the reflection geometry, and in this reflection geometry, the two theta angles are correspond to a region where you consider that the disorder is not so large. And if you are trying to measure protein, generally there is a resolution limit, and the disorders the disorder happens to be high for 2 theta equal to 90 degrees. So the best option would be to put the camera in transmission geometry. And this is so we haven't done that for protein materials, but we need to test that on our beamline. But I know for sure that there are also beamline at ESRF or in other synchrotron that they are doing some Laue measurement, but in this case they don't have a broad spectral band. They just have it comes from on an undulator, so it's a 1%, maybe 1% spectral band. So maybe from 6 kV to maybe 10 kV to 10.1 kV. So in our case, we have a large spectral band. So if we put a protein on BM32 and we are in transmission geometry where the Laue pattern is not suffering from the disorder, then due to the large spectral band of our beamline, then I think we should measure a too large number of reflections. So maybe it won't be possible to. It will be full of spots, and then it will be difficult to extract information from that. So one solution will be to move the detector a bit at larger angles. Could be a way. But maybe the disorder will be too high, and then so actually I don't know if we could find a compromise. Yes, a geometry that suits really the protein measurements, because we can't reduce the spectral band like this. It's not so easy. And we have to measure from 5 to maybe we can reduce up to 18 kV. From 5 kV to 18 kV, but I think it could be difficult. But I must admit that we think about that for a long time, but we haven't taken the time to test that.
Hello again. I think that there was a question relative to Ravi told me that you made a question about the dislocation nature. Is it possible to find the nature of a dislocation from the Laue pattern? So what is possible to do is to if you have a single dislocation, this is not really the case in real materials, but if you are able to isolate a single dislocation, you can measure the rotation field around it, and then you need to measure several Laue patterns around these dislocations. And then normally you should be able to, by measuring the fine spots displacement, you should be able to find, to have an idea of the rotation field, and then that should correspond to the theoretical field around the dislocation. But from a single Laue pattern, it's not so easy. So generally what people do is they assume, because they know quite well their materials in terms of mechanical properties, and then they consider that they will suppose that what they measure is edge dislocations, and these dislocations will store in some space, and then what will be in the signal of the Laue diffraction is sensitive to this dislocation storage, and then they deduce the dislocation density. So Ravi is finishing is smoking. So maybe for the we have started the work with Ravi to introduce the neural network. It was because we needed to have a fast tool to index complicated Laue patterns. Complicated, it means that we have several 10, 15 Laue patterns that are intricate on a single image. And also we needed to accelerate the indexing of a complicated single Laue pattern of with a large number of spots. For instance, what I've shown for the UO2 UO2 Laue pattern, we had several Laue patterns from UO2, but a single Laue pattern of UO2 is made of maybe I don't remember 200 spots maybe. And the idea of we had a project and we needed to index a Laue pattern with 700 Laue spots per Laue pattern, and then what I've shown you for the classical tools we have developed so far, it was too long to be used for the map, for two-dimensional map of zirconia in this case. So Ravi is ready.
Yes.
So the floor is yours.
Myself.
So okay, so I can start the presentation. I hope my voice is clear. And so basically, I will present quickly, 15 or 20 minutes to a small presentation to show you how the neural network works. And then I will also show you a demo of the graphical user interface that we have developed here that implements all those things that will be shown in this presentation. And wait, let me hit pointer. Okay. So before we go into it, I could quickly explain what a neural network or a machine learning based algorithms are. And since we are basically dealing with them, and there is a huge distinction actually. So in general, you have an artificial intelligence, which comprises of all these subcategories, which is called machine learning. And then the deep learning is another subcategory of the machine learning. So basically the whole idea of artificial intelligence is to make the process of analyzing your data or anything that has a pattern that it can be able to replicate or analyze from it. So the first technique that is often used in material science is the machine learning, because machine learning actually works based on the past experiences. So if you have any data and if you know what the data corresponds to, you can train a machine to analyze such data. So you're the one who's feeding information or you're telling the machine to learn or to exactly understand what it needs to learn from the data. Similarly, how humans, we do logical processing. So the same thing does the machine learning, whereas the deep learning is a subcategory of machine learning where we use these in-depth neural networks. That is, so here we don't provide any features. So there is no input from the user itself. So we expect the machine to learn by itself the patterns, if any, exist in the data set that we have supplied to them. So these are the two distinct classifications. So you can see it from this image that in the machine learning based approach, if you have a car and if you want your machine to identify and classify it as a car, there is an in-between process called a feature extraction where we as a human would have to tell the machine to look for a car to have a circular tires or a certain shape, and then the machine would train on such informations, and then it will tell you whether the given input is a car or not. Whereas in a deep learning based techniques, we eliminate this feature extraction process and we expect the deep learning algorithm to understand and extract these features that we do it manually actually. So these are the two distinct, and of course the machine learning technique has a huge wide range of techniques, and the one that is presented in this slide is not nearly complete. It is just a part of what exists actually. So you have several different techniques within machine learning. There is supervised learning where we supervise the machine when it is learning to verify whether it is going in the good direction or not. And then there is also an unsupervised learning where it gets really a little bit complicated, where we expect the machine to categorize and label by itself. So often in material science problems, we use supervised learnings. And then there's this other category of neural network that I said before. So in the current case, we have used a very, very subcategory called deep feed-forward neural networks. Of course, you can apply other types of neural networks to the same problems, but this is the one that we got good results with. So this is the technique that I will show in the preceding slides. So I can probably skip this part. This is the same as what Jean-Sébastien has already explained, that we have a micro-Laue diffraction setup here with a polychromatic beam of 5 to 23 keV. And so it's a spectrum of energy. And when you illuminate a crystal with such energy, you will see diffraction spots that you can capture with your detector. And since it's a penetrative technique, X-ray, so you can get signal from multiple grains that are underneath your surface actually. So in case of polycrystalline, as you would see here, that you can have multiple spots, and then the whole idea of Laue indexation is to separate these spots, identify them, and then calculate and obtain our structural refinement parameters. To give you a quick example, these are simulated Laue patterns that I've done it for a few of the crystals. On the left side, you have for a cubic symmetry copper single crystal. You can see that the number of spots is around 40. And the uranium dioxide that Jean-Sébastien showed in this slide before, it can have around a single grain could correspond to around 160 spots on the detector. Whereas as soon as you decrease your symmetry, or if you go for a lower symmetry like monoclinic zirconia oxide, a single crystal of zirconia, depending on its unit cell parameters, can have 500 to 1,000 spots. So when it is a single crystal, it's easier. You can, as Jean-Sébastien showed you, that the zone axes are apparently visible. So you can clearly index them without any difficulty. So even for monoclinic, if it is a single crystal, you can easily spot the zone axes and do the indexation process with the classical technique. Now imagine if you have a polycrystal for the same symmetries in the same crystal. If I've just added 5 grains now instead of 1 grain. So now this becomes a little bit complicated. You lose the zone axes actually. You cannot clearly see the zone axes. Even for copper, you can see that the zone axis is lost. And then there's an additional problem of overlapping spots. So you can in theory actually do a much bigger unit cell. But the only problem is that if you have a highly dense number of spots that are diffracting, and if they overlap, then it becomes really complicated to analyze them actually. So hence we try to go, for example, at the end case, I've shown around 2,600 spots. So the neural network that I'll show you today has been tested up to 2,000 spots. It works very well. In theory, we can extend it to also more than 2,000 spots. There should be no problem. But the only problem is that the spots that we see on the detector should be well resolved. There shouldn't be too much overlapping to create a streaking of Laue patterns. Then it becomes really complicated to find a local minima of the peaks. And this is the classical indexation process that Jean-Sébastien has already shown you. So these are the different steps that is involved in the classical indexation. You have a raw image. You find the peaks, you find the Larvae spots from these raw images by image processing, and then you convert them into your scattering angle space, the 2 theta and key, and then you arbitrarily select 2 spots out of these multiple spots, and then you hope that you will find them in the lookup table that you have created. This is a theoretical lookup table. So the process is similar to how EBST also indexes. So there is no complication here. The only problem is that you have to apply a lot of brute force, because in a single crystal, it's okay. You can find, obviously you will find 2 spots that belongs to a same grain, but as soon as you go into a polycrystalline material, the possibility of finding 2 spots that belongs to a same grain diminishes actually. So then it becomes, you have to try several number of spots, compare them with a bigger lookup table, and then to find a solution. So once you find your solution in the lookup table, you can simulate a Larvae pattern with the same parameters, and then you can overlap on top of your experimental Larvae patterns, and then that is how you will index it with confidence, saying that, okay, these spot corresponds to these HKLs. And the final step is, of course, the strain refinement. But before that, we need to be sure that the indexation is perfectly done. So the objective of the neural network is to not replace this whole complete process, but to just replace the second step of indexation, which is the most significant time-consuming one. So we want to index the HKL of the spots directly without going into this lookup table-based approach. And to do that, the idea is that we have used a deep learning-based neural network. So we would expect the neural network to find the pattern by itself. But since we already know the important pattern or the features that we are looking for, so we can already feed that information to the machine, thereby making the process a little slightly faster, actually. So here what we have done is, so here on the left side, you have your Larvae pattern. So to feed the neural network, what we have done is we take a single spot, and then we look at its radially neighbor distribution, actually. So we have taken, for example, a 555 HKL spot. So this is well indexed because it's a simulated Larvae pattern. So we know already all these spots and HKLs. And so we take the center point, and then we compute the angular distances between the neighboring spots defined by a limiting radius. And this limiting radius can be anything. It is user dependent. So for the moment, I've taken a 20-degree radius. So all these spots that are within the 20-degree will be classified in a distribution like this. So you have a sort of a fingerprint for any given spot. So now you will repeat this same process for all these spots, and then you will have a stack of histograms for each spots. And you can also make things complicated. So you can have a single crystal Larvae pattern. So as is shown on the top image A, this is a single crystal copper. And if I look at the spot 100, I have certain radial distribution. But now if I simulate a polycrystalline copper, now there are 3 grains in the image B. For the same 100 spot, the radial distribution changes actually. It is now slightly different because you have contribution from the second or the third grain that is also present in this distribution. And we can also make it more a little bit complicated by adding another phase actually. So in general, from the experimental patterns, you cannot really say whether the spot belongs to a copper phase or a silicon phase or any other material. So hence we have simulated such cases, and we are trying to feed the neural network to say that if you see certain distributions of angles around a spot, then this should belong to this material or not. And the parameters that I will show you in the GUI from this slide, would correspond to the limiting radius, the radius which is 20 degrees here. So you can define it to increase this radius to capture more heterogeneity among the spots or not. And also the bin width for our angular distribution. So the bin width is often fixed. So here we have used a bin width of 0.1 degrees. You can go lower or even higher depending on the quality of your Larvae patterns. And this is the neural network that we have used. It's a very simple classical feed-forward based neural network. So you have an input layer, which is a 1D vector, and then you have several hidden layers. So that's why it's called a deep neural network, because you have several layers in between them of different lengths. So basically the whole idea is that when I will feed my neural network some information on the left side in the X vector, in the Y vector, I will get the probability of the given input belonging to a certain HKL. So my output has values of HKL, as well as the value of I, which could be your material actually, if the pattern comes from a copper, or if it comes from silicon, or if it comes from any other material. So how would this translate to our case? So each fixed bin width is fed to one of the neurons in the neural network. And then in turn, during the training, the weights of these different 3 layers are optimized so that at the end we would get that. I know that the input is a 555 Laue spot. So my output should indicate that it is the 111 HKL belonging to a copper face. So since this is also a supervised learning, so we are training the neural network by telling that this pattern belongs to this HKL and this material. And so you can do this for n number of materials or any other complicated cases also. And similarly, the parameters that we will use in the neural network script would be what is the maximum HKL that we want to index, and also how many materials. So it could involve copper, silicon, or any other material that you want. And the other parameter is that since we want to explore also the complete orientation space, so we can generate a uniform distributions so that we make sure that the neural network has seen all different types of orientations or a case of them. So, and then we do the classical splitting of creating a training data set and validation data set that don't overlap. And then this is also a parameter that you can input while you're training your neural network. So that would be the number of orientations that we would like to generate. And these are some statistics that the neural network works for all different crystal symmetries from cubic to triclinic. And the impressive thing is the prediction time for a single Laue pattern. Everything is well within a second. So we can resolve the HKLs of each of all Laue spots within a Laue pattern within well less than a second, actually. So this process of the second step of indexation has now been reduced to less than a second. So we hope that with this one, we will be able to do a real-time indexation. So I will show you a case study, and then we will move to the GUI. So to show you how the neural network, the actual application of the neural network. So here we have a case study of a gallium nitride whiskers. So these are hexagonal gallium nitride whiskers, nanowires, which are placed on top of the silicon substrate. So below is a single crystal silicon, and on top is a gallium nitride, which were grown in lab. And you have different character also for these gallium nitride microwires. You have a bright face and then a dark face, which depends on the way that they were grown actually. So we'll be able, since Laue, with Laue diffraction, you can also spatially resolve the components. So we'll be also be able to see this heterogeneity between this bright and then the dark face. And how does the Laue pattern looks like? So if I take a single measurement of one of these spots that we have done, so basically when we do Laue diffraction, we do a raster scan. So just like EBSD, we do line scans. We go from left to right, and then we try to complete the area that we want to analyze with the beam size and then a given step interval. So for one of the measurement point, you can see that the Laue pattern looks like this. It has contribution that comes from silicon, and then there are several gallium nitride wires which are overlapping here. There are 1 or 2. So you have a Laue pattern, something like this. So classically, what you would do is you would index the silicon phase separately. You would remove the silicon phase, and then with the remaining number of spots, you will try to index them with a gallium nitride phase. Whereas here, what we have done is we have told the neural network, okay, my material has 2 phases. So it consists of both silicon and gallium nitride. And I train a neural network with such specification. And then now the neural network just requires this raw input. So it will convert it into scattering angle space. And then it will tell me that, voila, these are the spot that belongs to the silicon. These are the spot that belongs to gallium nitride first grain, and then the gallium nitride second grain, or the second nanowire. So now this process is completely automated. So there is no pre or post processing required of the data. And we put this whole thing into a loop and into a GUI, and this is what you will get that. With on the left, you have a scanning direction, which shows you the location of the beam every time it is scanning. And on the right, you have the phase which are separated. For example, it tells you that there is a silicon phase present here, and then it also separates the gallium nitride phase, the grain 1 and the grain 2. So this is something similar to what EBSD also does, that once you tell them that these are the material that are present, it will index and it will also separate them. So now the same thing can also be done with the Laue in indexation actually. And of course, the speed here is exaggerated. It is going much faster, but in reality, you can, one measurement of Laue pattern can take around a second for it to measure and then save the data. And then similarly, the indexation should be in real time. So we should resolve the Laue pattern as soon as the data is being generated. And similarly, the one other advantage is that you can extract also the strain components, as Jean-Sébastien has already shown you that you can get different types of the strain components, strain tensor components, and which is basically the deviatoric one. So from this one, we can extract what is the strain in the silicon phase as well as in the gallium nitride phase in real time. So there is no other processing that is required after the indexation. These are all being done in real time. And you can see that the strain in silicon phase is close to zero. It's close to the resolution of the Laue scheme, and which is in good agreement since there was no straining of the silicon layer. Whereas in the gallium nitride, you see in the epsilon 33 component, there is a heterogeneity in the strain distribution, which corresponds to the way that the wires were grown. So the bright phase has a closer to zero strain, whereas the dark contrast phase has a compressive strain, which is also in agreement. So this shows you that the capability of the neural network that yes, we can index complicated or multi-phase materials also without explicitly doing any other post or pre-processing that often takes days, if not months, to analyze such data. And so I will now go into the, so we have developed a GUI, and if you're familiar with Python, because the code is completely written with Python and it is available open source, so you can install it just using pip install LaueTools NN. So it's same as the LaueTools of Jean-Sébastien, but with NN to show that it is with neural network. And the principle and analysis after the indexation is completely similar to what Jean-Sébastien does with the software of LaueTools. And so to make it a little bit productive, I will show one case study with the GUI software. So I've taken this case study. So on the left, you have an image of a two-phase material, which is an indium bismuth and then strained indium. So the bright phase corresponds to the strained indium, and then the dark phase corresponds to the indium bismuth phase. So what we have done is we have taken an 100 by 100 micron area. And then we have scanned with Laue actually, a line and a raster scan, which is done. And we hope that with this, so what I've done is I've trained a neural network with these two materials. And we hope that the neural network will find these two phases and they will resolve and it will separate it along with the strain distribution. So I can now move to the, okay, maybe before I go, I can also show you some of the other examples that we can do. So it is not only limited to single crystal. For example, this is a case of a titanium. It's a polycrystalline titanium. Yes.
Maybe a quick question.
Yes. Yeah. Okay.
Is there a parameter in the machine learning process that takes into account changes in pressure or temperature as both to change the available spots in the certain area? Or if it currently applied can build up both ambient pressure and temperature?
So for the moment, we have not included temperature or pressure as a parameter during the input or during the training of the neural network, but this can be realized easily. It doesn't have to be room temperature. We can also train a neural network for a different lattice parameter that we're taken at a different temperature. So the whole idea is that if you know a law that defines your lattice parameter with temperature or with pressure, you can use that to simulate a Laue pattern and then train a neural network with it. And then so instead of just predicting the HKL, we will also be able to predict the HKL as well as the temperature or the stresses that could belong to this HKL or belong to the spot based on how it has moved. So yes, it should be possible, but it has not been realized yet. So this is one of the example of a polycrystalline titanium. On the left side is an optical image, and on the right side is a resolved Laue pattern index. And then we also have a case of a zirconia where you can have the Laue patterns can produce some streaking corresponding to slightly misoriented crystals. And the neural network is able to detect these two closely misoriented grains also, as you can see. It is able to predict the one and the second grain. Whereas with classical techniques, such indexation is possible, but it becomes super long. So all this is done within a second, the resolution of the HKL indexes. And so maybe I can go into the case study of the yes. All right, there is also a few other cases that I can maybe show quickly. So we have also done this on polycrystalline tungsten, where you can have more than 10 grains which are diffracting, and the neural network is able to detect up to 10 grains. But then we don't really calculate and show for all the 10 grains because the strain resolution changes with the depth of your material. So the idea is to just show the first top 5 or the top 3 intense grains that are diffracting, so you have good resolution of the strain. So you can do the similar type of analysis that you do with EBSD, like reconstruct your texture or see the local spatial texture inhomogeneity as well as the gradients. And this is also another study where you have the copper, micron copper pads which are embedded within the silicon. So the neural network is able to separate the silicon phase as well as the different copper pads that are present within them. And then at the end, you also get the strain distribution related to the silicon and as well as the copper. Okay. So, okay. So I will go into the demo of the tool. So let me share my screen. Okay, is my screen visible? I just take your time. Okay.
I think you should be okay.
Okay. So so here I have, for example, before we go into the tool, I can show you that we need a small config file to define everything, and then everything is automatic after that. So this is a config file that I've created for our case study of indium to bismuth and indium. So you have different parameters that most of them are optional. You don't really have to give, but the other ones are really required, such as the path to your directory and everything. So we can also speed up this whole neural network based approach, the post-processing of finding these orientation matrices and strain calculation by having more number of CPUs. So this you can define it by saying if you want to do a parallel jobs along with it. And then you define your main directory where your model and all related files would be saved. So I've defined, for example, here my directory would have a prefix of ESRF user meet. So we will see that how this will be created and generated. And then there is the material subsection. In the material subsection, you'll have to define what are the material that you want to index, or what are the material that you want to also train the neural network as. So in this case, I have defined 2 materials. So there is the material one, which is an indium bismuth. What is the symmetry of this material? And then the space group is really optional. If you don't have the space group, it's not really required. It is only used to create some symmetry matrices, but we can generate it with directly the hexagonal symmetry if this is not present. And similarly, I've defined my second material with a material 1 key, the indium epsilon, and it has a tetragonal symmetry. So this is also interesting that we are using this neural network to identify 2 different materials with 2 different symmetries. You'll see how it works. And so this is also applicable to, you can have n number of materials. So for the moment, the GUI only has 2 material as limits, but there is within the installation folder, there is also several notebook scripts that are provided with which you can have more than 5 or 6 materials. Also, you can train a neural network with that. And these are some of the training parameters that I've already shown in the presentation that would come here. Few of them are optional, so I will not explain them. For example, there is this maximum number of simulation, which describes how many orientation you want to train the neural network with. So this is the IPF map that I've showed before. So I'm saying here, generate me 500 random or uniform orientations that covers the whole Euler space. And then we will use these orientations to index the HKLs or to train the neural network. You can also include small angle misorientation. You can define an axis and an angle to say that your training data set should also include small misorientation cases because they can produce spots which are closer to each other. And then, so this is the parameter that defines your limiting radius and then the bin size. So here I've used a limiting radius bigger of close to 120 degrees, whereas in the presentation I've showed for 20 degrees, because it's better to have a much bigger angular radius so that you can have a better correlation of a single spot with its large neighbors actually. And these are classical parameters for machine learning. You can define your batch size depending on how much RAM you have in your computer, but 50 usually works for lower end computers also. And how many epochs you want your neural network to train on. Epoch corresponds to where all the 500 orientations that we have generated would pass through one loop of neural network training. So we are asking the neural network to train on at least 3 epochs, because the one other advantage is that since we have already provided features for the neural network to learn from, it can really train much quicker. It doesn't really need hundreds of epochs to train on it. Because the whole idea is that for real-time indexing or at the beam time, you really need a neural network to train within minutes so that you can start the prediction process when the experiment starts. And this is the parameter that defines how many n number of HKL that you want to detect. So I've kept, for example, for the hexagonal phase as 4. So every HKL index that has an HKL value less than 4 would be predicted by the neural network. And similarly for the tetragonal phase, I've kept it a little bit higher because the symmetry is lower than hexagonal. And then you have several other parameters for prediction, how many UB matrices you want to detect. So since I know that in my material, I have a silicon phase, I have an indium bismuth phase and an Indian epsilon phase. So I can have at any given point, I can have a Laue pattern which could compose of 2 different orientations. So I've asked my neural network to predict 2 orientations. And these are some technical things that would define how good the matching is and everything. So we'll not enter more deep into it. And there are also several other modes that are offered. So you can have a neural network prediction much faster or much slower, depending on how you want to index your Laue patterns. If they are very simpler cases like circular Laue patterns, graph mode it works perfectly fine. Or if you have a streaking or very close Laue spots, then you would probably have to probe a lot of different spots to really index them well. So, and the other important thing is this one, the softmax global, which is the accuracy of the neural network. So I can ask the algorithm to say that anything that has an accuracy predicted by the neural network less than 90% should be eliminated, because I don't have confidence on such predictions. So I'm saying that all the predictions which has an accuracy of more than 90% should only be considered for constructing an orientation matrix. This makes your processing a little bit faster, but if in case a neural network is unable to index a material, you can decrease this threshold. And maybe I can skip all these things because these are not really interesting, but these are all of these are optional commands that you want. The main command, the main input is basically your detector file that John Sebastian showed you how to create with LaueTools. You basically have the configuration of your detector and the geometry of your detector in this file. So we will use this data to simulate the Laue patterns as well as to when we try to index them. And then you also have to provide your experimental directory where all your data is, and then the size of your raster scan. Some of this can be automatized, but for the moment we have kept it. And okay, I will skip all these other parameters, which are not really important, but you have different options that you can define so that once you have defined it, you can really launch the neural network completely. And it is not really necessary that all this parameter has to be defined because by default, they are already set at the good values. So now I can show you the GUI. So this is our config file that we have, and this is what we would need when we will when we will open our GUI. So I'm not sure if the text is, how can increase the text size? No.
Maybe preferences somewhere.
Yeah.
Yeah, just on front.
Yes. Okay. Thank you. Okay, so okay, so I'm not sure if you're familiar with Python. If you're familiar with Python, then it should be easier to follow the terminal commands. Otherwise, it's not very difficult. So I have created an Anaconda environment that includes all my Python libraries called LaueNN. And then it's simpler. I just have to do pip install LaueTools NN since it's already installed in my computer, so it will just say that it is already satisfied. Once it is installed from the terminal, you can just type LaueTools NN and it should open the graphical interface. So here's the graphical interface. So all the other example parameter that I showed you is also present here in the example config with all the comments. So you can really copy and paste this to create your own config file or not. Once you have your config file, you go to the menu and you do a load config. So this is the config file that we created for our indium bismuth and indium epsilon phase. I will open it. Once you see this config file loaded successfully, you can do configure parameters. And in this one, it's basically all the same parameter that we define in the file. So if you don't have a file, you can directly also define it from the GUI. So my first material is the indium bismuth, and it has this symmetry. And all these parameters that we already defined in the text file is taken and is replaced here on by detector parameters. So the main thing here is the mode of analysis. So you can do generate data and training, or if you already have a simulated data, you can train on it, or you can just go into the prediction. So we'll start with the generate data and training. So we will basically simulate a lot of Larvae patterns, 500 Larvae patterns, as shared before, of different orientations. And we will train a neural network with that one. So first we have to build the 500. Once I do that, this button gets activated. I do generate training. So it is now generating the training data set, and we can see it in the folder. So it has created a new folder here, indium bismuth ESRF user meet. And in this folder, you have all the data that corresponds to your neural network model. So this is all, everything is written with Python. So you can access everything if you have a Python interpreter, you can really play around with the data and really see how everything is working. So it's not very complicated, and all the data is stored. So it should be accessible. It should take less than a minute to generate the data. So it is already, so if I open the training data set, it has all my data set of different orientations that it has generated, and it stores all the HKLs and everything. And the advantage of using simulation-based approach is that you really don't need a lot of experimental data. You can simulate as much data as you want, and then you can train a neural network on it. That's one of the biggest advantages here. So we have the data generation is completed. We have generated the data, and then it also prints you the HKL and how many occurrences there are. For example, the HKL -134 and all its corresponding equivalent HKL occurs around 1,200 times in the whole 500 simulations that we have done. And similarly, you have because I asked the neural network to only index up to 4 HKL. So you will see that none of the 3 HKLs maximum crosses above 4. You can also go for as many as you want. There is no limit really. It's just that the training would take a little bit longer time if you ask it to predict also much higher HKLs. And similarly, you have, the one other thing is that depending, because as you would see that the occurrences of each HKL is not the same. So this will introduce some bias in the training process. So to avoid that, we assign this neural network weight penalties. So the one with the highest occurrences will be given an weight 1. And the one with the lower weights, as soon as we scale it with the weights, so that we tell the neural network that all these HKLs are equally important. You should try to train on all of them and not just the one with the highest occurrences. And this is up to this is for the hexagonal phase, and this is, you have the tetragonal phase here. So we have around almost 95 classes of HKL that we have to train on. So I can just do train my neural network. And you can see that this is the model. It prints you all my model. It has my first layer with 1,200 inputs, and then my first dense layer, second dense layer, and third dense layer. And then at the end, output has 95 classes. You can already see that the validation accuracy has already reached around 93%. So within few seconds, we have already generated the data. We have already trained our neural network to a very good accuracy. Now this can be tracked here. If I open the folder, so you can see within few seconds, we have reached an accuracy of close to 94% in validation. So that means that we are now ready to predict. And once this is done, I can just press this live prediction with IPF map. So this opens me in another window, which will do the prediction. Since all the experimental path and everything is well defined in the config file, I really don't have to change anything in the GUI. I just have to press buttons. And before we do, we can also do this simple image-based analysis where I can check if my neural network will work on this data or not. So this is my 50 cross 50 scan that we have done with the Larvae technique. And each pixel here corresponds to a Larvae pattern. So if I right click on any one of this pixel, you will see the raw Larvae pattern that we have, as Jean-Sébastien also showed you, and you can do all the peak search and you can try to run the prediction on just a single Larvae pattern to see if your neural network is working with the parameters that you have defined in the config. And these parameters can also be modified here slightly to see if you can help the neural network to deal with it. Once this is done, this really gives you an idea that whether your technique will work or not. You can also do this calculate image similarity. So within seconds, it will analyze each Larvae patterns nearby, and it will try to tell you how different spatially the Larvae patterns are, the recorded Larvae patterns are. And this should more or less match with our indium-2 bismuth's optical image that we have done. So there we go. So we can clearly see that the intensities here tells you how similar the Larvae patterns are in spatially. So we did a scan like this, and we can clearly see the boundaries between the two different faces. So if I click on within this face, you have this Larvae pattern, and if I click on this one, you have a different Larvae pattern. So this also gives you an indication of how you can better train your neural network, whether if you have 2 grains or multiple grains. So these are just tools that are available to make it a little bit easier. Once I'm very satisfied with the training that I've done, I can just say that, okay, I want to predict 2 grains. I can use the multiprocessing power and I can just press predict and plot. So it is basically launching all the processes. So each process will deal with one image. It will try to predict on it, and then it will use the prediction HKLs as a result to compute the orientation matrices. And from the orientation matrices, it will refine the strains, and then it will plot everything here. So I can check, for example, I've asked it to plot 2 grains. So we can already see few of the Larvae patterns are being indexed here in real time. So I can check for the second grain. The second grain is basically the indium bismuth. From the material index, you can see on the right side, 1 corresponds to indium bismuth and 2 corresponds to indium epsilon. So the value of this one is 2, which means that all these Larvae patterns which are resolved here belongs to an indium epsilon phase. If I check my first orientation matrices, the value is 1, which tells you that, okay, these are the Larvae patterns that are coming from my indium bismuth phase. And I can verify this also. I can right click on any of these pixels. It will show me how good the indexation is. So the black spots are my experimental Larvae pattern, and then the red spot are the simulated one, which were generated based on the predictions. So you can see that the match is very good. We have been able to match everything with the experimental patterns clearly, and you can also see the HKL of your prediction and what is the orientation matrix of your indexed grain, and all other different statistics that could be useful. And similarly, if you're not satisfied with certain results, you can also do a middle mouse button to really play with all these parameters and say that, okay, I want to re-index this pattern again because I'm not satisfied with the neural network's results. And you can propagate these new settings to all of your remaining indexations. Apart from that, you can also do several statistical analysis. For example, on the IPF map, you can do a rectangular selection box that will give you all the strain distribution of the pixels that has been indexed. So you can spatially and locally, you can characterize your microstructure to say that, okay, my strain distributions are really heterogeneous or not. Or if you prefer a line distribution rather than a box, so you can also draw a line on it, and then it will interpolate to the nearest pixels and it will plot you all these statistics that belongs to the line. So you can do several different The indexation approach is very simple. It uses a simple neural network-based algorithm. Apart from that, you can do several other post-processing online while the indexation is happening to really fine-tune your next experiments or the one that you're already doing. So that's the whole objective of developing such techniques. So you can also see the strain distributions, actually the deviatoric strains in one of the phase. This is for indium epsilon, which is slightly higher. It's around 0.2%. Whereas if I check for the indium bismuth phase, the strains are close to 0 actually. So there is almost no strain. So I can maybe stop this so I can show you one of the results directly. So this is basically a real-time indexation of how it would happen when you're collecting your experimental Larvae patterns. You can launch this tool at the same time, and it will start the indexation process as soon as your data is available to it. Maybe, or the other thing is that once you have done with your analysis, you can also save all this data. Everything would be saved there, and you can again just do a load results. So I can show you one of the previous results that were run on this. I just have to load my results file, and then you can see the results that were done with the indexation. You can clearly identify the Indian bismuth phase. We also plot the IPF colors, the matching rate, how good the indexation is. Again, it is completely interactable, so you can clearly see how well the indexation has done. If you're not happy with certain places, you can re-index them. So I can check the second grain also, which should belong to Indian bismuth. So in this case, you see that this pixel is not indexed, one of the black spots in this one. So as a post-processing, I can click on it, I can right-click on it, and I can verify and I can re-index this one, and this will update all my data along with it. So I can do a background correction. And similar to what Jean-Sebastian showed actually. So the idea is to now detect peaks and then see if I can. So I had used an intensity threshold of 100 before. Maybe it is not enough for the neural network. So I can try 85. I do a peak search. So it shows me where all the peaks are. It has detected me all the peaks. So I can zoom in and I can show you also. So this corresponds to a peak which has been identified. Yes. So this also does the same Gaussian fitting. It is basically the same tool that Jean-Sebastian has shown. And now I can also decrease my softmax threshold. I'm saying that, okay, maybe 90% is a too strong limit. I will say anything greater than 85% of accuracy predicted by the neural network should be considered as a solution. Then I can run the prediction again. And I will say, okay, the neural network was not able to predict. It does nothing. So maybe I can also optimize few of the peak search parameters. And so we will see if it works. I can increase the number of spots that it is probing. And if I run the prediction again, nope, it doesn't work. Okay.
Is there a tolerance?
Yes, there is a tolerance. So I can maybe, yes, I can decrease the tolerance. And we will run again the prediction. Hopefully it will predict something, but no.
The tolerance in angle.
Yes, the tolerance angle is around 0.5 degrees. But yes, I can. Yes, we can increase that to 1. So before I try, I think this corresponds to that. Yes, why not? Okay, so I will increase the tolerance angle. Apparently, it is not working this way.
Well,
Maybe it is a partial Laue pattern, or not all the peaks are well resolved. It could be that. So I can increase my parameter, but this is now too many peaks. Still, it doesn't work. Okay. So there is this other option also where you can use this index with neighboring matrices. So what it will do is for this pixel, it will check its neighbor matrices and it will try to use the same orientation matrices to index with them. For the moment, it is not implemented completely, but the whole idea is that if we can use the neighboring orientation matrices to index itself, so we can now try with an increased angle tolerance. So I will just modify in my config file that the grain detection tolerance should be a little bit higher. Okay. 0.1. Okay. 1 would be okay, too high, but yes, we'll see. Yes. And now I just have to reload my config. That it is done. I can config and I want to do a prediction, not training. Let's load the results. This is for the indium to epsilon phase. Okay, so I will try with slightly relaxed constraints for the peak search as well as for the neural network. do my peak search, has detected all the peaks, then I can. So now, okay, it has tried to index something as soon as we have increased the angle tolerance, but apparently it is not a very good indexation. You can see that the matching rate is around 15%. So one other problem could be that when you have a lot of spots that could be noise or that are not really detected well in the peak search algorithm, then your neural network has never really been trained on such data. So one other idea would be to train your neural network also with some noisy patterns, a lot of noises or a lot of some pixels which does not really correspond to a Laue pattern, and then to see if it really works. So in general, it works, but we can also try. I'm not sure if this would help. Okay, no, apparently no, it is not able to detect this grain. But the thing is, if you see the nearest grain, which corresponds, I think, which also is similar, which is not so different. So I can, or maybe I can show directly the indexed Laue pattern, which is the same one actually, and the non-indexed one and the indexed one. Apparently it is less noisy, the indexed one, whereas the
it's the same.
it's the same pattern. So I can use the nearest neighbor. So it should also work. So sometimes it can also fail, but the thing is that during post-processing, you can run again a loop to say that, okay, index with the nearest ones. But in more or less, it works. So you can see that it has completely indexed everything. And you can do a lot of different types of analysis to calculate the strain in a given certain volume or in a given line distribution. And this really makes your experimental stay easier. Yes, I think if you have, I hope I've been able to demonstrate the tool. And so even if you have any Laue patterns that you have done or Laue campaigns, you can try to use this tool and see if it works for your case. We have tested this for more than 2,000 spots, so it should be able to work. We have results for several polycrystalline material also, where there are more than 10 grains refracting. So yes, give it a go, and it's very simple to use. It's not complicated, and if you have any questions or any technical thing that you want to include, or you can always contact me, and yes, we can find a way to improve the tool more. Actually.
Okay, thank you, Ravi. I think, yes, there's time for discussion and also questions. Feel free to unmute and ask your question directly. No particular question, or maybe I can go back to the conclusion, and yes, I think yes, maybe just. Yes, I think we can conclude. So maybe just find one of the last slide. Yes. So this could be the conclusion of this presentation in two parts. So at the beginning, we have shown that so for a decade we have a beamline with the instrumentation to do micro Laue diffraction, and for the moment we have such a performance in terms of beam size. In the future, what we have a better instrumentation to higher flux. So we expect to have the flux multiplied by 10 in 2 years or 2 or 3 years, even yes, in 1 year or 2 years maybe. And this we are able to do so wide beam experiment, wide beam diffraction but we also have we have already the way to measure the energy, and as a reminder, you know that if we are able to measure the energy, we have the complete access determination of the full strain and full stress, and which is very important. So full strain or full lattice parameters for fundamental or technological applied materials, and full stress for the engineering part. What we saw the experiment, we can perform some non-destructive experiments, so in situ experiments, so you can really follow how the microstructure or how the structural parameters evolve with an external parameter. And this is really open to large community, large fields of studies. So from metallurgy, functional materials, and this is really suited for devices, electronics, or small objects, mechanics. There are some users coming from mineralogy and cultural heritage. In this field, we can do better than before, and also so for the biology, for the protein, so I think we need to have some inputs from the community to really see how we can adapt our instrumentation to satisfy the needs of new communities, so especially the biology. And so we are making some fundamental and applied sciences. Users are in these areas, and so basically what we have to remember that we can measure the local structure in materials, so inside the materials also. So we can do some 3D evaluation of the structural properties. And for when the materials is not so disordered, this is a very, very powerful tool to do some metrology. So I mean for microelectronics devices, photonics devices. It's a nice X-rays, and in this polychromatic mode, it's a really nice tool to do metrology and also to control the location of the stress heterogeneities, and so to enhance the reliability and the durability of materials, and obviously to improve the understanding of materials. So I think we have covered most of the thing I wanted to show you. Maybe we miss some points. So don't hesitate to ask us, to contact us for if you want to test your sample, if you want to write a proposal. And I would like to add that we will close the beamline for the micro Laue station. We will close it next year for several months in order to complete our refurbishment of this upgrade of this instrumentation. So I would suggest you to for the call that the next call in a few weeks. Only a part of the semester will be available for the users. So let's say only 2/3, and then for the next call of September. Clearly, there shouldn't be so many beam times for the Laue. So if you have ideas of proposals, and so I may recommend you to apply for beam time for the next weeks. But we are also very open to for discussion, and also to make some tests in your sample. in order to increase the quality and the feasibility of and the reliability of the data. Okay, there is a question. Yes, we got some photo. Oh, no, this is an answer. Okay, sorry. Okay, I think we can conclude like this. Ravi and I thank you for your attention, for your questions and your interest for these techniques. I hope. Thank you to John also for very good insight in particular for this biological studies. So I hope you will enjoy the user meeting, and I hope to see you, to hear from you in the next days and weeks. Okay, see you. Bye bye. Take care of you, and bye bye.